Thanks for the introduction. Hi, everybody, and thanks for inviting me here. So I wasn't able to make it to the keynote yesterday, but I understand Rust already came up a bit, and I think Martin had some nice things to say, which is good. He sort of teed me up. But I'm going to start sort of from the beginning in this talk telling you a little bit about what Rust is about and why you, as a Scala programmer, might care about it. So I titled this talk Rust Confident Productive Systems Programming. And I want to start by just breaking down each piece of that as a way of explaining sort of what Rust's mission in life is. So I'm going to start from the end and work backwards. So let's start with systems programming. So what I mean by this is low-level programming, where you have a high level of control over hardware, over the way things are laid out in memory, over exactly what's happening when. You don't have a runtime system, no garbage collection. You're programming more or less to the bare metal, right? So this is the domain traditionally of languages like C and C++. And as we'll talk about later, there are certain kinds of applications that really need this kind of low-level view on things. But systems-level programming is used for all kinds of things, like building out high-performance web servers like Nginx or Apache and so on. OK, next, productive. So despite being a low-level language in terms of the kind of hardware control that Rust gives you, it also tries to be a high-level language in terms of the kinds of productivity it provides. So a lot of this will be familiar coming from a language like Scala, which also strives to give you a lot of productivity. So Rust has high-level iterators. It has pattern matching, something akin to like case classes in Scala. It has a first-class package manager called Cargo, which makes it very, very easy to manage dependencies through a central repository, and tons of other goodies. I won't talk a ton about the productivity elements, but the message is basically, if you were to come to Rust from Scala, you wouldn't miss that much from the language, the kind of high-level expressive language that you're used to. OK, the last piece, I think, is the most interesting aspect of Rust, in particular, in combination with the other things Rust is trying to do. And that's confident, right? So this is about how you feel when you program in Rust. You feel confident. And that's an unusual way to feel when you're doing systems programming. And I'm gonna show you exactly why later, in case you haven't had the pleasure of feeling very afraid when you're doing systems programming. But in particular, Rust provides a bunch of guarantees that you don't usually get in the system world, like no seg faults, no dangling pointers. You have a lot of protection against memory exploits that typically happen if you're programming in C or C++. But it goes even further. I don't know if you're familiar with the concept of a data race. I'll be talking a lot about it later in the talk. But it has to do with concurrent programming. And Rust gives you a very strong guarantee about getting concurrency right. And so it goes, it's giving you confidence that you don't even tend to get in higher level languages, despite being really low level. So these are sort of the major themes the talk is going to cover from a few angles. We'll be coming back to each of those. But I want to just spend a little bit more time exploring the space of systems programming and why Mozilla cares about it and why you might care about it. So I do work at Mozilla. If you know Mozilla, you probably know it through the Firefox web browser, which is its main product. And you might be curious why Mozilla sponsored the creation of a programming language. So the answer is, browsers compete very heavily on performance, right? In a way, browsers are kind of like operating systems. You're running all kinds of applications inside them. They have to handle media. They have a lot of performance constraints. And part of the reason that Chrome has become so much more popular than Firefox is its better performance, right? So it's really vital from Mozilla's perspective to get back in the game of competing on performance. But at the same time, your web browser is kind of the interface between you and a whole bunch of hackers that are trying to get your credentials, get your credit card information, and so on and so forth. So safety, security is also vital for browsers. Historically, though, browsers are written in C++, so they're optimizing for performance and not giving you a lot of guarantees around safety. And so you get these emergency updates when exploits are found and people are hacking into your browser session. So coming from that perspective, Mozilla started investing in Rust to build a new language to replace C++ that starts to eliminate some of these trade-offs. So it gives us competitive performance, but provides much greater guarantees against security exploits and other problems that have plagued web browsers in the past. And we've been using this to build a new browser engine called Servo, which is now starting to land actually in Firefox. So throughout the rest of this year, more and more pieces of Rust code will be landing in Firefox and powering the new engine. OK, so I said that browsers need a lot of control. I've been talking about low-level control. Let me give you a little bit more concrete idea of what I mean by that. So I'm going to walk through just a really simple example from C++ that'll illustrate a number of sort of guarantees that C++ gives you when it comes to control over the machine. OK, so first of all, in C++, when you have a vector definition like this, the way that this actually works out in memory is you're guaranteed that the basic data of the vector is allocated on the stack. OK, so a vector here has a pointer pointing to a buffer that actually contains the data of interest. And then it has length, which tells you sort of how much of that buffer is actually valid data, and a capacity, which tells you how much room there is, right? So all of that sort of metadata is allocated right on the stack. And then the contents of the vector itself live on the heap just one hop away. And then in this case, I've got a vector of strings. And strings, of course, are yet another vector. And so you have the same pattern repeated again. So each element of the outer vector contains these sort of three pieces of information over and over and over for each string. So to start reading a string in this vector, you only have to follow 2 pointers. Okay? Now that's a lot different from most higher-level garbage-collected languages, where everything basically is heap allocated, everything is 1 pointer away, everything has a uniform representation to a first degree of approximation. And this kind of thing can have a really big performance impact. OK. Another interesting thing that C++ gives you is lightweight references. So what I mean by that is the ability to point directly into the middle of an object without copying anything out. Again, if you know C or C++, this is kind of an obvious thing. But in most garbage-collected high-level languages, you can't really do this. Instead, you're having to copy data out of an object every time you want to sort of point into it. And again, this kind of thing has important performance ramifications. And then finally, there's a piece of code. There's something going on in this code which is not written explicitly, which is that at the end of this block, vector goes out of scope. And when that happens, it's automatically deallocated. And you know that. As a programmer, you know exactly when this is happening. And so that's, of course, very different from a garbage-collected world where it'll be deallocated at some point. And this applies not just to memory, but to all kinds of resources. Whether you're managing files or sockets or anything else, you have a lot of control and knowledge about exactly when it's around and when it's not. OK, so that all maybe seems nice, interesting, could give you some performance. But it's also very dangerous to program in this kind of world. So I'm going to walk through a simple example of how things can go wrong. So here again, we have a vector. Let's say that initially we've got just one element in it, and its capacity is 1. So we take one of these nice little references directly into the contents of the vector. And then we ask to push a new element onto the vector. But we're out of space. So what we're going to do is allocate a new buffer, copy over the existing data, and then push on the element we wanted. And then we'll change the data pointer to point to this new buffer, deallocating the original one. OK, but there's an obvious problem here, because we still have this lm pointer hanging around that was pointing at the old buffer, which has now been deallocated. And if we try to actually output it or read from it or whatever, anything could happen. If you're lucky, your program will crash. If you're unlucky, a hacker will steal your credit card information, right? So this is the concern. And this is a very, very simple example. Lots of compilers can catch very obvious cases like this. But in general, when you're doing systems-level programming, this is the kind of thing you have to worry about all the time. And so you end up programming in a very defensive, fearful way. And that's one of the things that Rust is aiming to change. So I want to pause here and analyze a little bit what exactly went wrong in this example, because it's going to give us the foundation for understanding how Rust helps you get it right. So there are basically two ingredients to the problem I just showed you. First of all, we had aliasing. And by that, I just mean we've got more than one thing pointing to the same thing, right? So we had a data pointer pointing to the original buffer and an LM pointer pointing to that buffer, aliasing. Aliasing by itself is fine, but we're also using mutation, right? So we're changing the data pointer without changing the other aliases or even being aware of them. And we're also deallocating the original buffer without being aware of those other aliases. So it's really that combination of aliasing and mutation that gets us into trouble. Sorry, I accidentally skipped backwards. OK, and we'll come back to this theme of mutation and aliasing together causing problems over and over again. So one last sort of high-level piece before I start really diving in. Why do you care about any of this as a Scala programmer? You're certainly not about to go rewrite your entire app in Rust, and I'm not trying to tell you that you should do that. But if you're programming something that's supposed to work at high scale, you've probably hit some performance problems, or maybe some reliability problems. And I don't know, I mean, I did a lot of Scala programming actually during my PhD days, and I was doing a lot of high-performance stuff, and often got very frustrated when the JVM sometimes would sort of optimize my code the way I wanted, and sometimes wouldn't. And it's very unpredictable and hard to actually guarantee strong performance. So what Rust can offer to you is the ability to write components, critical components, where you need low-level control, or you need high reliability, or you need high performance. You can write those components in Rust. Rust doesn't have a runtime system, doesn't have a garbage collector. It's very easy to use Rust together with other languages. It looks just like C to the outside world, so you can call it easily from Scala as well. Right? So the message is, use the right tool for the job. Rust is a new tool for certain kinds of programming, and you can bring it together with other work that you're doing in Scala and other languages. OK, and I'll just mention Rust sort of is a combination of ideas from a lot of different languages. Cyclone is sort of an academic language that first tried to tackle this safe systems programming space. But we borrow ideas from lots of other places and hope to borrow more ideas from Scala. There are a few, but we'd like to do more. OK, so the rest of this talk is going to proceed through several pillars of Rust's design. And each of these pillars has to do with eliminating a trade-off that we used to think was fundamental. All right, so the first one is, how do you get memory safety, so avoiding those kinds of crashes I was talking about, if you don't have a garbage-collected language? So Rust answers that question. How can you have concurrency without having all the usual pitfalls and bugs that show up as data races? Rust gives you an answer there. How can you provide abstractions without paying a lot of overhead? Again, Rust gives you an answer. And stability without stagnation is about how we evolve the language without breaking code that relies on previous versions. And the overall message here is Rust is about hacking without fear. OK, so without further ado, let's start with the first pillar. So the key new concept in Rust is ownership. And I'm going to walk through exactly what ownership means, but let me give you just a very quick summary. So everything in Rust is owned by default. So if you are talking about a vector, that vector is an owned piece of data. If you pass it around, you're transferring ownership of it. But then there's a way to borrow temporarily ownership of data. And particular types like scalars, integer types, floating point numbers, and so on, are considered copy data, where basically we say ownership is not significant for these types. So if I give you an integer, I still have the integer myself. I'm not transferring ownership to you. And then we also have C++ style destructors for basically when no one owns an object anymore, it's automatically destroyed. And as a programmer, you can predict exactly when that's going to happen. OK, so let me step through each of those points in a little bit more detail. And in each case, we're going to be solving this problem of aliasing and mutation in one way or another. So let me start with owned data, which is if you just pass a type normally, it's owned. Ownership allows mutation, but it doesn't allow aliasing. It's a unique thing. I own the vector, no one else does. OK, so let me show you in code what that actually looks like. So this is some code in Rust. Looks vaguely similar to the C++ code. So here we're allocating a new vector on the stack. And notice the layout here is the same as it was with C++. We push on an element. That creates a heap allocation. We push on another element. All is well and good. OK, and now we're going to pass this vector to the function take. And take has as its argument type vec event. And so the way you should read that in Rust is, oh, sorry, is there a question?
Could you just clarify when you say ownership, what is the actual owner? Scope or a thread or what is the owner here?
OK, so the question is, when we talk about ownership in Rust, who is owning? Is it a thread? Is it a scope? What is it? And I think the simplest answer is it's basically a scope, like a block, but that gives you a notion of thread ownership, as we'll see later. So I think the answer will be more clear as we look through concrete examples. OK, right. So yeah, so I was saying by writing vec event as the argument type here, we're basically saying, please give me ownership of the vector. And so when that happens, what happens at runtime is we make a shallow copy of the vector, so those 3 words of information, to live on the stack frame for take. And that represents sort of the full ownership of the vector. The original sort of vector, copy of the vector on the stack is now unusable. Its ownership has been transferred. It's just a stale bit of data. But notice, of course, we didn't copy the vector contents itself, just the sort of metadata. Now, at this point, we start to execute take. It does whatever it's going to do. And then at the end of its scope, vector goes out of scope, or vec, I should say, and is deallocated, right? So we popped the stack frame, but more importantly, we deallocated the contents of the vector on the heap, right? That's the key point. Now, here's where things could go wrong in C++, right? The ... Basically, if we kept trying to use vec in our original copy, we'd be using a dangling pointer at this point. But we can't in Rust, because the compiler actually enforces an ownership discipline. So if we tried to write, for example, vec.push here, the Rust compiler will give us an error and refuse to compile the program, saying, you've moved vector. You can't use it anymore. And this very simple discipline rules out basically all of the traditional bugs of systems programming. So use after free, double moves, dangling pointer, you name it, this ownership strategy accounts for it. But it's not a very nice way to program, necessarily, passing ownership all the time. Usually, when you're calling a function and passing it an argument, you're asking it to use that argument temporarily, do something, but you want to keep using whatever that data was after the fact, right? So it's not that common to want to fully pass ownership of objects. And so we have other options in Rust, which are called references or sometimes borrows. Okay? And these come in 2 varieties. I'll start with shared references. Shared references allow aliasing, so you can have multiple of these references pointing to the same object. But if you have a shared reference, you're not allowed to mutate through it. So we rule out this combination of aliasing and mutation. OK, so let's go back to this example and use a shared reference instead. So things look pretty similar, right? We allocate the vector. We push some elements onto it. But now, instead of passing vec itself, we're passing ampersand vec, a reference to a vec. So two things have changed, right? The function we're calling now in its signature says, please give me a temporary borrowed access to a vector. And at the caller, we're saying ampersand vec, so we know we're just handing out temporary access, but we'll still have ownership of vec available after that function call completes. Okay, and the runtime implications are a little bit different here as well. So a reference is just a pointer. So now instead of copying that metadata onto the stack, we just push a pointer for calling use. Use does its thing, comes back, and now the only thing that's destroyed is the reference, not the contents of the vector, which means we can go on to continue using the vector in the original function. Okay, but if we want to avoid the problems with C++ that I showed you before, we really need to rule out mutation, right? Because the initial example I showed basically kept around a pointer to a vector, into a vector in particular, while that vector was mutated and its buffer was replaced, right? So the way we rule that out with shared references is by just disallowing mutation, right? So in the use function, where we said we're taking a shared reference to a vector, if we try to push, if we try to assign to an element, if we do anything that requires mutable access, we will get an error from the compiler saying, you only have shared access to this data, you can't mutate. And again, this prevents the kind of bug in C++ we were talking about before. And I'll put a little asterisk here. I'm giving you the sort of common case version. There are edge cases where you can safely mutate, and Rust gives you ways to do that. Right, so it's not a 100% strict discipline. There are ways to bend the rules, and I'll show you that a little bit later on. Okay, so that was shared references. And then finally, we have mutable references, because sometimes you want to pass an object to some other function who's going to mutate that object, but not destroy it. Right, and in that case, you're not allowed to hand out multiple of those references at the same time. Only one can be at play at once. Okay, so an example of that is if we have a function basically for copying one vector to another. The source vector, we only need a shared borrow of. The target vector, we need a mutable borrow, or mutable reference. Okay, so we designate that right in the arguments. And I should say, actually, one of the things I find nicest about programming in Rust is the fact that just looking at the signature of a function like push all, I know exactly what things could possibly be mutated by that function and which things couldn't be, right? So I have a lot of knowledge about what's going on, which, coming back to this point about programming with confidence, this lets you dive into a code base that you don't know very well and very quickly learn a lot about it and have confidence in what you're doing because you know that things won't be changed behind your back. Okay, so because we have a mutable target vector, we're allowed to call push on it. So that's great. And the way this is going to work, both the from and the to parameters are just pointers on the stack. So we'll have they're going to point to a vector that's stored somewhere, which in turn will point to its buffer on the heap. And then as we walk through each element of the vector, we're going to get a pointer into that buffer, and we'll start expanding the buffer of the target vector one by one. Okay. Question, what if the two vectors are the same? Well, in this case, if we were already at capacity, the first time that we try to push on an element to the vector, we're going to copy the buffer over and invalidate the earlier buffer, which seems like the same kind of problem we had at the beginning with C++, right? We get a dangling pointer. So that seems bad. How does Rust rule that out? Right, so I mentioned before that mutable references give you mutation but don't allow aliasing. So concretely what that looks like is if I had a caller that was trying to create at the same time a shared reference and a mutable reference to a vector, we get an error that says you can only have one mutable reference at a time. And so we just can't call this function with the same vector in both arguments, and so we avoid this problem. Cool. So one way to think about this is, and this is a sort of golden rule in Rust, like if you have a mutable reference to a piece of data, at that point in time, you are the only piece of code who could possibly be accessing that data, which means in particular no other thread could be accessing that data, a point we'll come back to later. All right, now I want to give you just a bit of a flavor for how to scale this up, because this probably seems pretty simplistic, and you're probably worried about, can you actually program in this model? Is it too restrictive? So I want to show you an example that shows off how borrowing is a kind of temporary thing, and you can borrow in all kinds of different ways over time. So here, again, we have a vector. We have a for loop that is iterating over that vector. And in the body of this for loop, right, we have a reference to an element of the vector, and we try to mutate the vector at the same time. That's bad, right? That's behavior we want to rule out. And Rust will rule it out because basically calling the push method requires a mutable reference, but we already have a shared reference taken out in the same scope, right? So for the same reason as the last slide, this is not allowed. But after the for loop, we're guaranteed that none of these shared references are live anymore, right? We're only referencing inside the vector each time around the loop, and then once we escape, there are no more references. And so at that point, we're allowed to push onto the vector. And so in general, these kinds of borrows, these creation of references that we've been talking about, they last only for a block that they're within, sort of in the default case. And so that allows you to do a little bit of sharing for a while, then stop that, then do some mutation, then stop that, and then go do some more sharing. OK, another point, again, just to give you a sense of how this scales up. Suppose you have a data structure with a couple of different fields in it, and you want to sort of separately hand out the ability to mutate those fields individually, right? Can you do that? So here what I'm doing is taking a mutable reference to each field rather than to the struct as a whole. And the cool thing is that Rust is actually able to reason about this. It understands that X and Y are distinct locations in memory, and so the rules about aliasing don't apply to them if you're talking about them separately. Right, so so this block basically says the duration of the borrow for X. This block is the duration of the borrow for Y. But this is fine, because what we're saying is if you're trying to make two loans in a region, right, if you're creating these references, either the things you're loaning out have to be disjoint, talking about different fields, or they have to be shared references and not mutable. That's it. Okay, but that actually gets you quite far. And then one more step. So a lot of what happens in practice in Rust is we build on this foundation that I've showed you, but we don't require the compiler to understand absolutely every way of arranging things and slicing up memory that we might be interested in. That's not realistic. We need a way to extend the sort of safe things that Rust can do. So here's an example of a function we want to write, which takes in a slice, which is like a view into a vector, and a midpoint, and gives you back two slices, basically splitting the slice at that midpoint. But in particular, it comes in with mutable access to the whole slice and wants to give you separate, simultaneous mutable access to the subslices. Now, this should be OK because those subslices are disjoint, right? They're broken at the midpoint, so there's no actual aliasing here. But unlike the fields I was just talking about, Rust doesn't have the ability to reason about array indexing and arithmetic and that kind of thing. So how do we do it? Well, we break the rules, but in a controlled way, right? So Rust gives you a notion of an unsafe block, where basically you are allowed to break the rules of the borrow checker. But the key point is to use this successfully, you want to provide a safe interface so that for any arguments you could possibly give to this function, it will not actually create an unsafe condition at runtime. Like it will never create a dangling pointer. It will never create actual aliasing and mutation at the same time, right? So this is tricky. Like whenever you use unsafe, that's a piece of code you need to audit very carefully. But the point is you can seal that up. You can audit that piece of code just once, be confident that it is in fact a safe piece of code, and now you've basically extended what you can do with safe Rust. Right, so this is a function that's in the standard library. We're very confident that its unsafe implementation follows the actual rules of Rust. But notice that the signature, like to guarantee the safety here, we're taking advantage of the way we can talk about ownership in function signatures. Right, the fact that we know coming in, we're giving the unique way of accessing this slice. So that means coming out, we can give the unique ways of accessing these two subslices. Okay, so that's the basic story about memory safety without garbage collection in Rust. Now let's look at one of the other, I think, most unique aspects of Rust, which is confident concurrency, right? So concurrency without data races. So concurrency in Rust has a kind of interesting history. When Rust was first being designed, the idea was to have a very opinionated story for concurrency. Basically, no sharing of state between threads. You would just do isolated message passing. So threads would pass ownership through messages, and that would be the end of it. But over time, we've actually gotten a much richer story that says concurrency is not really a built-in thing in Rust. Instead, you can do all kinds of different concurrent programming through libraries that you build up, representing different paradigms. But all of these libraries guarantee freedom from data races, which I'm going to explain in just a second. So they're all leveraging the ownership system to give you a more confident style of concurrent programming. Okay, what is a data race? So a data race is a particular kind of race condition in a concurrent program. Right, so in general, race conditions are just situations where you have like multiple threads running concurrently, and you're not sure what order things are going to happen in. They're racing to see who gets there first. Races in general are okay, but data races are always bad. They always represent a bug. So a data race is a situation where you have two different threads accessing the same piece of data. At least one of the threads is trying to write to that piece of data, and you have absolutely zero synchronization going on. And by synchronization, I could be talking about a lock, or I could be talking about low-level hardware primitive, like compare and swap, if you know what that is. Like that covers a really wide range of things, but basically you're giving the compiler a heads up that, hey, there's a race going on here, please compile accordingly. Now, C and C++ compilers assume that your program has no data races. If you make a data race, your program has arbitrary semantics. It can do anything. And again, hackers steal your credit card, right? And these things definitely get weaponized in practice. The reason that happens is the compilers want to optimize your code really well. And to do that, in general, they have to assume that most of the data you're accessing is not accessed concurrently by other threads. That allows them to do the best kinds of optimizations. But that assumption is broken if you don't give the compiler a heads up when data might be modified by other threads. OK, so another way of talking about data races, right? I said two threads, same data, that's aliasing. One thread is writing, that's mutation. No synchronization. Those three things give you a data race. But by now, you should recognize that the first two of these things are sort of the bread and butter of what Rust is all about. So the strategy for controlling data races, for guarding against data races, is the same as the strategy we've used for memory safety all along, ownership. OK, and part of my message here is shared state concurrent programming is not evil. A lot of people make this argument, and rightly so. Like, it's historically full of pitfalls, very easy to get wrong. But I think the Rust perspective on this is that the problem isn't that you're sharing state, it's that you're doing it without realizing it. It's when you're accidentally communicating between threads and you didn't know this was happening. And so when Rust talks about no data races, what we really mean is it's not possible to accidentally share state without knowing that it's happening because of the ownership system. You could still get synchronization wrong. You can still have concurrency bugs, but you had to at least make an attempt. You had to at least know that concurrency was happening, which is already miles ahead of where you get with most programming languages. OK, that's all pretty high level. Let me walk through just a couple of concurrency paradigms and how they play out in Rust, so you see more concretely what this looks like. OK, so we'll start with message passing. Message passing works purely through ownership. It's really simple. So we have a parent thread. It creates a channel. That channel has two ends, a transmit end and a receive end. OK, so now we've got those allocated on a stack. They point to some buffers on the heap. Great. Now, we're going to spawn a child thread. And I'm not going to take a lot of time to go through this notation about move and so on. The key point here is we're passing a closure. The body of that closure is going to be what the child thread runs. And move just means basically everything referenced by that closure is moved. The ownership is transferred away from the parent thread to the child. OK, so let's say the child looks like this. It allocates a vector and sends it on the transmit end. Well, because it mentions the transmit end, and we're saying we want to move ownership, we are actually taking ownership of the transmit end away from the parent. OK, so concretely, that stack data is invalidated. TX now lives on the stack on the child thread as well. And now we're ready to communicate. OK, so now when that child thread is running, it's going to allocate a vector, maybe put some data in. And when it calls send, what's going to happen is we will make, again, a shallow copy of just the metadata of the vector and send that across the channel, okay, without copying the actual contents. So this works exactly the same way as that very first function call I showed you at the beginning where we're transferring ownership. Right? So we're not having to copy huge amounts of heap data around, yet we're guaranteed now in this paradigm that the vectors that we're passing back and forth on this channel are always owned by exactly one thread at a time. So once you have that vector back in the parent thread, you can confidently program against it knowing that the child thread is no longer using it. Right? So this is, when people talk about isolated message passing, this is what they want to do. But the nice thing about Rust is it lets you build that paradigm and actually guarantees that you do it the right way, right? That you're not actually mutating things behind your back, right? I don't know of a lot of other languages that give you that kind of guarantee, low level or high level. OK, that's message passing. Let's look at locks. So here I have a function that is going to just increment an integer in a shared integer in a thread-safe way. OK, so we have a mutex type in Rust. And there's some pretty interesting stuff going on here. Normally, mutex types don't take a type parameter. But here we're saying mutex of int. What does that mean? Well, we're actually saying up front what data it is that the lock is protecting. And in fact, when no one has the lock itself owns that data. OK, so when we initially create this mutex, we're sort of transferring ownership of an integer into it. And then when we call lock, what's going to happen is we get back this special kind of object called a guard. And a guard basically gives you access to that integer, mutable access, but only for as long as that guard itself is around. OK, so in particular, guard has a destructor that will release the lock. So we can use guard as if it were a pointer. So we can use it to increment the integer, and that works just fine. But at the end of this block, when guard goes out of scope, the lock is automatically released. Now, the point here isn't just, oh, I didn't have to write lock release. That's not a big deal. The point is that I can only access the data protected by the lock while I hold the lock. Because the only way I have of getting at that data is through the guard. And as long as the guard still exists, the lock has not yet been released. So the important thing is I literally have no way to release the lock other than destroying the guard. And once I've destroyed the guard, I've given up access. Right? So so this actually is a way of guaranteeing that you're using locks correctly. And again, this is a way of doing shared state concurrency, but I can tell this is happening because I'm operating on mutex event types, right? If I just had a ampersand mute int, then I would know, in fact, there's no concurrency happening, right? And that's the default case in Rust. So you can't share state implicitly. It's always explicit in some form or another. OK, let me show you one other paradigm, which is basically programming algorithms in sort of divide and conquer style that are accessing disjoint pieces of memory in different threads, right? So quicksort is a typical example of this. Here we're using that split at mute function I mentioned before. So we have this initial view, mutable view into the vector, and we're going to break it into two disjoint subviews of the vector. And this is the sequential version, right? So I just recursively quicksort on each of these subpieces. OK, fine. What if I want to do it in parallel? Well, that's easy, right? I just run those two subcomputations in parallel. Now, you can do that in any language. The thing about Rust is when I'm doing this, I'm guaranteed that those two subthreads are actually accessing and mutating disjoint pieces of memory. So again, I know that I'm never accidentally sharing state between them. I know that the result they're going to produce is exactly the same as they would if I ran them sequentially. So I can confidently inject parallelism and take advantage of multiple cores without worrying that there's going to be some concurrency happening behind my back that I wasn't aware of. OK. And there are many other concurrency paradigms that you can code up in Rust. I'm happy to talk offline about that. I want to make one last point about concurrency, which is this whole notion of thread safety, right? So the usual state of affairs is if you're lucky, the documentation for some class you're working with will tell you which methods are thread safe and which ones aren't. Hopefully you looked at the docs. Hopefully they were there. Hopefully you followed the rules. In Rust, riffing on a theme here, all of that is actually enforced. So going back to the send function for channels, for example, you can construct a channel of any type that is send. And what send means, send is a trait in Rust. I'll talk about traits in a second. Send basically means that this piece of data is safe to transfer to another thread. So I'll give you an example that comes up in Rust. We have two ways of doing reference counting in Rust. Reference counting is kind of like a lightweight form of garbage collection. One of them is thread safe, and hence slower, and one of them is not thread safe, and hence faster. So you would like to use the not thread safe one as much as you can, but if this were C++, you'd be really worried that you'd accidentally leak it to another thread and get a data race and then crashes, exploits, and so on. With Rust, not so, right? As soon as you try actually sending this to another thread, you'll get a compile error. And this is not like a hypothetical example. We've had cases in the Rust compiler itself where buried deep inside a data structure was one of these non-thread safe pointers. And at some point 6 months later, we start to parallelize that bit of the compiler and suddenly get an error message that says, oh, wait, it's not thread safe, right? Even though by that time, the person doing this work had long since forgotten that there was this thread unsafe reference counted thing buried inside the data structure. So this really does help. OK, so I'm running a bit low on time. I'm going to pick up the clip a little bit. The next pillar of Rust is abstraction without overhead. So Rust has a trait system, which is similar to traits in Scala, but has some important differences. It's more like type classes in Haskell, if you know about those. But it's the main way that we do abstraction in Rust. And for today, the main point I want to get across is that with Rust, traits give you a way to decide between static and dynamic dispatch. And I'll explain what that means in a second. So here's a simple example of a trait. You define a trait. It's like an interface, again, sort of like Scala. Inside a trait, you can have things like associated types and methods that talk about how they're borrowing the type that implements the trait and so on. The key difference from Scala is that you can implement a trait for a type externally to that type's definition. So I can introduce a new type and implement it for, or excuse me, I can introduce a new trait and implement it for existing types. I'm not going to talk too much about that difference in the talk, but I'd be glad to talk offline about it. OK, so once you've defined a trait, there are two ways of using it. You can use it as a bound, so that's when I'm saying, please give me a type T that implements the iterator trait. In that case, I get static dispatch. So what that means is, every time the use function is called with a different T, the compiler will actually generate fresh code that's specialized to that particular T. Now, of course, the JVM does this kind of thing automatically for you, but there are limits. And sometimes when things get large, you hit those limits, and all of a sudden your performance falls off a cliff. With Rust, it's guaranteed. You're telling the compiler, please generate a separate copy of this code for each T, much like templates in C++. Okay, and so then when you're calling the iterator methods inside use, they're actually just calling directly, statically, whatever that type's implementation was. On the other hand, you can use dynamic dispatch, which is more like using traits as objects. Right? So here you're saying, I only want to compile one copy of the use function, and at runtime, I want there to be a vtable. I want it to be passed an object. And when I am going to call a method, I will just, at runtime, figure out what actual code to call. Right? And you really need both. Like, this object viewpoint is important if you want to put a bunch of things in a collection that have different concrete types but all implement the same interface, right? That's bread and butter object-oriented programming. So you really need both. But I guess the point about abstraction without overhead is particularly this static dispatch style lets you program in a very slick, productive, high-level way and be guaranteed that you're going to get high-performance code out the back end. Right? So here's a simple example of doing a dot product. With iterators in Rust. Again, lots of languages have iterators like this. So we've got two vectors. We're sort of iterating over both of them and doing a multiplication and then a sum. This guaranteed gets compiled down to some very efficient tight loop, which is using SIMD at the hardware level. So basically like parallelism to hardware level parallelism to walk over these arrays. Doesn't matter if you don't know what this is saying. Point is, it's fast. It's fast, and it's guaranteed to be fast. It's not fast just because you got lucky with the optimizer, and if things got a little bigger, it would stop generating this kind of code. And there's one more point to be made here, which is we can start putting these different ingredients together. So there's a library called Rayon in Rust that actually has a lot of similarity to the Scala collection types, where you can choose to iterate over things in parallel. And so we can now do this dot product with thread-level parallelism and like hardware-level data parallelism, SIMD. You could say that same kind of thing, again, in Scala and C++ and other languages. The difference in Rust is I can freely change from iter to pariter while confidently knowing that I won't change the meaning of my program, because there can't be some extra concurrent sharing going on behind my back. Right? And so this really lets you be a lot more ambitious with the kind of systems programming that you're doing. You can use parallelism more. You can use thread unsafe things more because Rust has your back. All right, final pillar, stability without stagnation. So this is basically a piece more about the community and policies and process and how we develop Rust. So if you followed Rust development at all, the 1.0 release is fairly recent. It came out in 2015. But Rust was under public development for a long time before then. And up until that 1.0 release, the Rust language basically broke your code every day. We were very aggressively iterating on the design. And so it was critical that when we actually published a 1.0, we sent a clear message that going forward, your code will continue to work in new versions of Rust. And so in particular, we wanted it to be the case that people would never dread upgrading the Rust compiler. They might have to change a small thing or two. It's very, very difficult to change a language at all without breaking some edge cases, but we can guarantee that the fixes are very, very limited. So it's a sort of hassle-free upgrade. So that's the stability we want to achieve. That's very important for Rust getting actually picked up in production usage. But the concern is if you pivot too hard in this direction, you lose your ability to actually evolve the language. And I know that this is something that the Scala community has struggled with over time as well. So let me tell you about how we do it in Rust. So since Rust was sponsored by Mozilla, we followed the browser-like train model, right? So we actually have different release channels of the Rust compiler, just like release channels of a browser. So we have a nightly channel, beta channel, stable channel. But before you get into any of these channels, you first have to get consensus on a design. Okay, so if you want to extend the language, the first step is to write an RFC, request for comments. Here's one of the first ones I wrote when I joined the team. And a key point here is that every change of any substance to the language has one of these. It doesn't matter who you are, whether you work at Mozilla or anywhere else, you cannot land a major change to the language without publicly proposing that design and having a public discussion around it. And we've had to learn through trial and error how to build a process around this that works well with the community, with the broader community. Because on the one hand, like, you don't want to get bogged down in endless discussion. You know, you're never going to get absolute unanimous agreement on a feature, but it's really vital to listen to people. There have been a number of things where members of the core Rust team, you know, had an idea in mind, and it turned out actually there were better ways to do it, but it took really listening and debating for a long time with the broader community to realize that. So one of the key rules that we've come to adopt is the no new rationale rule. Okay, and basically what this means is there are teams of people in the Rust world who are responsible for making decisions about different aspects. There's like a language team, standard library team, tooling team, and so on. But those decisions can never be handed down with some new rationale that came out just at the time the decision was made. Whatever is justifying that decision has to be publicly discussed beforehand. And what that means is basically we work together as an entire community to get on the same page about what the trade-offs are, like what the facts on the ground are. If you do this, it has this consequence. If you do this, it has that consequence. And the role of the team is to evaluate those trade-offs according to their value system and vision for Rust. That's the thing that you're never going to get unanimous agreement on because people value different things, right? But we should be able to agree on the facts on the ground, right? So the idea here is no new facts, no new rationale at the time a decision is handed. It's just a matter of saying, OK, everybody agrees about the trade-offs, and the team feels like this is more valuable than that, and so we're going that way. OK, so once you actually bring an RFC through that process, you can start implementing it and land it in the compiler. So the first stage is it lands in the nightly compiler. And we call features in the nightly compiler unstable, meaning that they can break your code because they're liable to change, right? We learn a lot in the implementation process and feedback as people start using these features. So the key thing is the beta and stable compilers, they're produced every 6 weeks, just like Firefox. And you can only use stable features on those channels, right? So if you are conservative, if you want to make sure that you can freely upgrade Rust and not have to worry about it, use the stable compiler, and we'll give you that guarantee. If you want to live on the bleeding edge, you can use the nightly compiler and unstable features. You might break, but you'll sort of know what you've gotten yourself into, right? So again, the promise is if your code compiles on stable Rust 1.x, it should also compile with a minimum of hassle on stable 1.x+1. OK, so what about this minimum of hassle bit, right? That seems like a heck of a loophole. So we want to make sure that we sort of tie our hands behind our back in the right way here. And the best way we came up to do that is what we call the elaboration rule. You can tell academic background. So the idea is really simple. Basically, the kinds of changes I have in mind here are things like the type inference system changes a little bit, and suddenly you need to have a type annotation somewhere where you didn't before. Or a new method got added, and suddenly there's an ambiguity about which method is being called in a certain context, and you have to disambiguate, and so on and so forth. All of these changes have a particular form where it's about a new ambiguity being introduced, and there's a way to be more explicit that avoids the ambiguity. And key point, you can change the code to make things more explicit and have code that will work across both versions, old and new. That's absolutely crucial because it means as these changes roll out, you're not splitting the ecosystem. There's a little bit of work that people have to do to disambiguate their code, but once they've done that work, their code will then work on either version of the compiler, and other people can build on it. And so that's the sort of crucial constraint around stability. And we've been able to do quite a lot of evolution while obeying this constraint, right? Now, you'll notice I have been talking about the Rust 1.x series. There's some question about, will there ever be a 2.x? What would that mean? Does that allow for more dramatic breakage? That's an open question in the Rust community, and I would love to hear about Scala's experience and sort of what you've learned. I think the way we're leaning right now is there may be a 2.0 eventually, but we would try to keep extremely close to this style of guarantee and make it so that the compiler would be able to handle both 1.x and 2.x series code at the same time. So again, you don't split the ecosystem. But that remains to be seen. And with that, I will leave you with the overall pillars of Rust. So confident systems programming. Thank you.
So a question in multiple parts. I imagine there are some types of things that are difficult to work with in the borrow checker, like persistent data structures, for example. I'm assuming you, given your background, you know what I mean. So I see those being quite difficult. So the first question is that the case? The second question is, could Rust support some kind of optional garbage collection at some point to make this easy to work with? And the third question, the one that everybody loves to ask, is high kind of types. What's the story?
All right. Awesome question. OK, so first question about persistent data structures. So I have not personally investigated persistent data structures heavily, but people who have found that actually they're not as bad as you might think in Rust. You can do them reasonably easily. But I think there is a more broad question. So like when I was first learning about Rust and actually like interviewing for the team, I asked, how do you make a doubly linked list? That seems to require aliasing and mutation sort of fundamentally, right? And so there are a bunch of examples like that don't fit very naturally in Rust's ownership model. And I think there are open questions about how best to handle this. So like we have answers for graphs and for doubly linked lists and for all these things. There are lots of different patterns. There are things like the reference counted pointers I mentioned and so on, where you can express these data structures without giving up performance and with a minimum of unsafe code. But it's definitely something we would like to get stronger at over time. But I think our experience has been you can get surprisingly far without having to reach for unsafe. And a lot of these kinds of data structures can live out sort of with a safe abstraction in a library. OK, your second question was optional garbage collection. This is a vital question for Rust because we care a lot about Rust's adoption, and as I pitched it to you all, a lot of that adoption is going to be driven in like module by module styles, not wholesale rewrites. So people are really excited about using Rust together with JavaScript, for example, for those core pieces where they really need performance. But then you need to integrate into the JavaScript garbage collector. And that happens to also be important for building a web browser, as it turns out. So again, it's a work in progress. There are designs, there are RFCs I can point you at, but it hasn't landed yet. The tricky thing is, like, I think a lot of people, sort of see this whole thing about Rust as, oh, well, you only care about it if you can't tolerate garbage collection. If you have garbage collection, you have safety, and so who cares? But that misses all of this stuff about mutability and concurrency and all these other guarantees, right? And so just adding an optional garbage collector isn't the whole picture, right? And you could easily lose a lot of Rust's other benefits. So again, interesting open questions, we're working on it. Higher kinded types will be coming to Rust within the next year to two. And there are RFCs about that. Again, happy to talk offline.
Could you talk a little bit more about integrating Rust with other languages, particularly JVM languages?
Yes, absolutely. So there are basic, of course, two directions of integration, right? There's you've written a Rust component and now you want to call it from the JVM, and you've written a Rust component and it needs to call into your JVM-based code. So I think our story is best in the case where you're writing a standalone Rust component and calling it from another language, because Rust can basically expose C-style APIs, and that's how all languages integrate with other languages at bottom, right? So that's pretty straightforward. I don't think there's been a lot of work in the Rust community on going the other direction with the JVM. There is work on doing that with lots of other languages, JavaScript, Ruby, Python, and so on, and I would love to get that effort going on the JVM side as well. So if you're interested in that, please let me know.
So I feel like the dream, or at least my dream, is to write pure functional programming and have it be low latency and performant. Do you feel like mutability? Do you feel like this is a stopgap solution because we're not there yet in the state of the art, or do you think that mutability is fundamental? We're always going to need it, or we'll just never be able to write really low latency code in pure FP?
Interesting question. So, I have spent my time in Haskell and sort of appreciate what it gives you, but it's worth noting that even in Haskell, you have mutation just in controlled ways through monads, right? So my feeling is that actually fully pure programming with no mutation whatsoever is a non-starter. Not just for low latency stuff, but just in general, it's not expressive enough. And I think Haskell started out without any ability whatsoever to mutate and very quickly had to add it on, not just for performance, but just to get work done. My feeling about, I guess the theme of this talk has been, the problem is the combination of aliasing and mutation, right? That's where code gets really hard to reason about. And so I don't see Rust as a stopgap. I see it as really giving you the tools you need as a programmer to know when mutation is happening, know when aliasing is happening, control it, and minimize it. But I think it's really important to have those tools available whether you're doing low latency or high latency programming.
What do you think Scala could learn from Rust, either at the level of the language or maybe the standard library or the development process?
That's an interesting question. So I think that there have been some experiments in Scala around something like Rust's ownership system or various ownership disciplines, controlled mutation, and so on. So sort of adding on to my answer to the last question, I think that kind of control is very valuable as a programmer, and I think it's worthwhile in the Scala community to see what could make sense in Scala to provide these kinds of stronger guarantees. In terms of the community and evolution and so on, I'm not well versed enough in how Scala is developed to sort of critique it. I can say that the RFC process that we follow in Rust is hard and it's slow, but I have found it very valuable to not follow a kind of benevolent dictator model, but really have to get buy-in from a large set of stakeholders and fully hear people out. It definitely can slow us down, but I think we wind up at a better place in the end. So it's been the right choice for Rust. I don't know if it's the right choice for everybody, but it's, it's something I would be more than happy to talk about with leaders in the Scala community. Cool. All right, thank you so much.